Welcome to specifying and fitting models. We're going to focus first on just a basic regression model. So we're going to start, what is regression? I've worked at this job long enough that I know everyone at some point in their life took algebra and learned y equals mx plus b. But we're going to just do a quick refresher on what is regression. And then we're going to talk about the standard least squares modeling platform in JMP. I'm not going to go into the nitty-gritty detail of how to build a perfect model, not that there is such a thing, but I'm going to build a model and I'm going to just talk a little bit about what sort of information does that model providing us. And then we're going to spend some time looking at some features and some little tools and then some things to look out for. There are certain assumptions that go into a standard least squares model that if we're not cognizant of, we may unknowingly violate. And so we think we have a model that is widely applicable to maybe a larger data set, but we have missed the mark because we thought something was true or whatever the case may be that actually wasn't. And then we have solutions when those particular assumptions can't be met. And we're going to talk specifically about normality of our response and multicollinearity, which basically means the model can't disentangle all those factors. And so when one changes, it's not certain if the other one's changing because of that one or if it's independent. So in those are the two broadest or most important assumptions. When those can't be met, we have some other tools to use. And so we'll kind of wrap up by looking at a tool that helps address that. And we're also going to look at a tool in that unfortunate situation where you maybe have a lot of factors, but not a lot of observations. And so that's going to kind of be how we run through this. So let's get right into it. And we're going to make this nice and big. So what is regression? Whoa, that didn't look good. Let's try that. There we go. So basically, we're trying to relate an independent to a dependent variable. So as I change something, what is that response? So when we fit a model, what we're doing is we're trying to fit a line that explains the maximum amount of the variability. So here we have some blue data points. We have a red line. This is the regression line. This is the equation. And so over here on the right, we have the slope. And that means for every unit of OD, we move to the right. We go up 0.5284 units on the Y. And then this first number is our intercept. And so if we project this all the way to 0, it's going to cross at 4.099. And what we're trying to do, like how that line gets drawn, is we're trying to minimize the distance of all of these points to that red line. You can imagine if the line was something like this, then these points up here would be very, very far. And so the sum of those distances would be much higher than it's currently drawn. And likewise, if it was more like this, we'd kind of be in the same boat. So what we're doing mathematically is we're trying to fit a line, this red one here, that minimizes the distance of all these points to that line. This is a very simple case. We're just looking at two factors. But when we perform standard least squares regression, we can look at multiple factors. And so that's what we're going to do. So I'm going to show an example where we're looking at a continuous response. And what that means is the response can be plotted on a number line. It has a magnitude. It's not an ordered response like first, second, third, if we're thinking about a race. It's not a categorical response like pass or fail. Those all use the same, kind of the same techniques, but they would fall under something called ordinal or nominal logistic modeling. And so if that is your situation, a lot of what we're going to talk about, you can apply to that, but it will look just a little bit different. And so as I mentioned, and I apologize, I moved to JMP 18 and my text got a little smaller. I should have changed this before. So hopefully you can read this okay. So we can handle main effects, interactions, quadratics, polynomials. Basically, if our factors, we think there's some curvature in our response, or if we think there is some interactions where if I change one factor, another factor's effects change, and you'll see all that. So if that's not completely clear, don't worry about it. But we have to, we're assuming that the response is normally distributed, so a bell curve, right? And so if our response, that's not a great line, but it's something more like this, then that's problematic. And so we'll talk about what we can do in those situations. And then I'll highlight the Box-Cox transformation, which I find is a really useful tool when we don't have a normal response. So we're going to look at data from a designed experiment. And so this is looking at some responses for manufacturing tire tread. We're really going to look at this abrasion term. And so we have a number of factors, just 3, and then we're going to look at abrasion. So once we build our model, which I'll show you how to do in just a moment, this is what the output is going to look like. The output will vary based on the appearance you select or the identity, which I'll show you how to change that. But this is pretty much the most common output. But you can turn everything off and on as you desire using the red triangle options. So we have an actual versus predicted. The red line is the model. The pink shaded region is our confidence interval. And we can see our data points. And this blue line is our mean. We can see we have an R squared of about 0.92, which is good. And then this data model has already been cleaned up to show our factors. And you'll notice all of them have a p-value of less than, very important difference, less than 0.05. And what that means is we have 95% confidence that the effect of these individual factors on our response did not occur by chance. If the p-value is greater than 0.05, say 0.06 or 0.6, we don't have that certainty, and the response, the effect on the response could just be random. And so we want to remove terms that have a p-value greater than 0.05. At least that's the practice I generally use. There's some debate about that. Just to reduce noise. We want a model that is free of as much noise as possible. Moving on down our report, we have some information on lack of fit, F ratios, etc. It's been a long time since I took statistics. And so sometimes, even though I work with this stuff day in and day out, whenever I'm confused, I go up to my question mark. And as you mouse across this report, you'll see different things are turning teal. And so if I click on this, it's going to open up my web browser and take me directly to a web page that describes what these statistics are, what's in this table, what it all means. And I use this far more than I care to admit as a jump systems engineer. But, you know, you can't fit everything in your brain all the time, and I just can't seem to recall things like I used to. So this is a really, really helpful tool. Moving on down, we have our residuals. What a residual is, if you're unfamiliar or unsure, it's basically taking the distance from the point to the line. So if I click on just that point, and I love dynamic data linking in JMP, it makes it so easy. So I clicked on this first data point, and this data point is, I don't know, maybe about 105, and that plots maybe, I'm not even gonna venture to guess, maybe 90 something. It's 7 units above the slope of this model. If I look at, say, this one, it's considerably below. And so this is just telling us that kind of the spread of our data. What we want is, if we were to project all of these points onto our y-axis, we'd want to see a normal distribution. And if I squint, I would argue that we see that. We have a lot of data points that are crowded right about the line, with just a few that are off the line. And we see these 3. We don't want to see patterns. If we see like a sinus, whoops, that didn't work. See like a sinusoid, or all of our points are high and then all of a sudden they all drop below, that usually means that we're missing something. There's something else going on with our data that we have not captured in this model. And so looking at this, I would argue that this model has explained the variability. And this pattern right here we're seeing is because they took replicates in this designed experiment. So the 2 areas that I tend to focus, well, I guess 3 areas. First, I look at this effect summary. This is always where I start. I always come down then to the parameter estimates. The reason for this is I love this column. We talked about multi-collinearity, and this is where we're going to see a red flag. This does not show up by default. And so to turn it on, you're just going to right-click anywhere on the table, go to columns, and turn on variance inflation factor, or VIF. And because this is a designed experiment, we would assume that all these values would be 1, because it's designed specifically to disentangle the effect of all of our factors on our response. But if you're working with real life data, it's messy, right? And so I always want to come here and make sure that I haven't overlooked something. If I have a really big data set I'm unfamiliar with, I might first throw it into the multivariate platform and just look to see, are there any highly correlated variables? Sometimes I forget, and this catches it for me. So VIF can be small, around 1. It can also be very, very large. A VIF of about 10 is roughly equivalent to an R squared of 0.9. And so when I see my VIFs getting up to 8, 9, 10, or sometimes I've seen 50 or 100, that tells me that there's some multi-collinearity going on that I have not accounted for. So I either need to do a deep dive and try and identify which of those variables are correlated and make, using my subject matter expertise, decide which ones to remove. But if I can't, then I've reached a limit within the standard least squares platform. The other area I look to a lot, and I'm going to again make this bigger, is the prediction profiler. And so if you've used JMP for any amount of time, you're probably quite familiar with the prediction profiler. And so what this is showing me is a visualization of the underpinning equations that are my model. I don't know about you, maybe you have this gift, but when I look at a model, equations, sometimes my eyes go a little cross and I have a hard time understanding. Like I can see a slope and I can see an intercept, but when there's 5 factors and I'm now looking at 5 slopes, 5 intercepts, it's hard to really wrap my brain around what's going on. This is what the prediction profiler is for. So what it's saying is if I enter these values in red into my model, then this value on my Y in red is the mean likely response. And then these blue numbers are that 95% confidence, and that's what the shaded region is. And it's interactive, which I love. And so I can move this around and say, okay, well, if I bump my silica up to about 1.5, I can expect my abrasion to be about 143. Maybe silane's expensive and I want to decrease that. Well, now my abrasion goes down. Is this the trade-off of reducing costs worse the loss in that abrasion magnitude? And that's something I can decide. The model's not going to tell me that. I have to use my subject matter expertise. The other thing it'll show me, and I want to draw your attention to this part of the graph here, is it shows me interactions. So you can see when silica is very high, I have a moderately positive relationship between sulfur and my response. But as silica decreases, it reduces the effect to 0. Now it doesn't matter what my sulfur magnitude is, it has 0 effect on my, my abrasion value. And as I keep going, it starts to go negative. So that's really nice to see. Now, one of the new features I really like in JMP 18 is we can now add some new information to this. So I'm going to come to my red triangle on my prediction profiler, and I'm going to say data points. So now I can see my data points, and you'll see they actually change in kind of the intensity of their color as they get closer and farther from the model fit. And I can also turn on overlaid interactions. So what these lines are showing me is what is the range of possible relationships between this factor and other factors based off those interactions. So you can see in these two plots, those lines are basically parallel, kind of saying they're going to move up and down. But this one over here is almost reminds me of like a fan, like a little hand fan, right? And so as I move this around, we can see we go to that minimum. And as I increase, we go to that maximum. And so we can kind of get a sense of how these interactions are going to play out using these two features. And so I think this is a pretty cool new feature. It's something I've always wanted to see. All right, so there's two questions. One is, what is VIF? The VIF is variance inflation factor, and it's going to give us a term to explain whether or not we have multicollinearity. And that just means whether or not we can disentangle the effects of different factors relative to our response. And then there's a question about, can you extrapolate in profiler? Yes, you can. In standard JMP, in standard least squares, you can turn on something called extrapolation control. And so we can turn a warning on. And then if I were to say, stretch this out and go out into no man's land, you can see now it says possible extrapolation. And so what it's saying is you're trying to make a prediction where you have no data to back this up. So I am very reticent to extrapolate in a model. But if I'm going to just, for a lack of a better term, play around with the data, I certainly want this to be turned on so that I know. And so in standard JMP, this is available in standard least squares. In JMP Pro, extrapolation control is available, I believe, in all regression models. It might be other predictive models as well. I would need to double check on that, but I'm pretty sure it is. Okay, so that's kind of the high overview of the standard least squares model report. Now let's construct this. So I'm going to go to Analyze, Fit Model, and we have 3 values. And I want to look at interactions and quadratic effects. And so those are just modeling terms to understand, is my factor, does it have a straight linear response, or maybe more of a parabolic response, or a second order polynomial? And then I also want to look at interactions. So we saw interactions. As I move one factor, does it have an effect on another factor? We can do that very easily using something called a response surface model. And so what I do is I just highlight my 3 factors. I go to macros and I say response surface. It automatically adds all of those. And then I can throw abrasion in my response. And I can, by default, it's going to take on standard least squares. I mentioned earlier about what I see in that initial report. That's controlled by this emphasis. So there's a few different options here. If I 99% of the time just use the default. Again, if you go there and it doesn't look the way you want, just go to your red triangle and you can turn different things off and on. So go ahead and run that report. And you'll see this initially looks a little bit different. I'll move it right over here. And it's driven by these additional factors. So I mentioned that I like to remove all terms that have a p-value greater than 0.05. And so I don't want to just grab them all. In this case, there's only one. But let's look at this second value from the bottom at 0.496. If I remove this first term, that's now jumped up. And that's why you don't want to just, if you have a lot of terms over 0.05, you want to grab them all at once and just remove them. Because as you strip noise out of your model, some factors that look like they have no statistical significance will actually kind of percolate and rise to the top, and you'll realize they do. And so a best practice is to remove these one at a time. We're seeing that happen in real time. There we go. And so now we have identical models. If I really like this model and I want to save it, I can just go to my red triangle, save the data table, and I think we would all agree this is a really cool model. And so now I can go to my data table and I have a really cool model. I can just click that script and boom, I'm right back to where I started. All right. So what happens if my model is not normal or my response is not normal? And we can test this. So I'm going to come back to my data table and I'm just going to open up distribution and throw abrasion in there. So here it is over here. And then I'm going to go to my red triangle next to abrasion, go to continuous fit, fit all. And it's going to give me an ordered list of what is the most likely distribution rated by this AICC variable. And so then it gives me a likelihood of one versus another. And so we see the first one is log normal. And so normal is kind of near the top. There's not a lot of data here. This is a relatively small DOE. So I might be okay getting by and just assuming it's normal. But if I want to be certain, what I like to use is the Box-Cox transformation. So what the Box-Cox transformation is going to do is it's going to calculate an exponent that you could, to transform your response, that's going to get it as normal as possible. And so it makes it very easy to use. So I'm going to go to my red triangle, factor profiling, go to Box-Cox Y transformation. That opens up a new report platform. And it's saying if I take my, transform my Y to the 0.705 power, I'm going to get that as normal as possible. So you might think then now I have to go to my table, create a new formula column, take my response to the 0.705 power. It's much easier than that. We can just go to the red triangle and say refit with transform. It's going to confirm that that's what I want to go to. And then it reruns that for me. And in this instance, it doesn't make a big difference. And so if we compare the model, the R squared is 0.92, the R squared is 0.92. So, you know, in this instance, maybe it wasn't necessary, but really I just wanted to show you how cool that is. And so now if we go back to the Box-Cox, you'll see now it's saying it's nearly 1. And so this has been a good transformation. And what's nice about this is it doesn't change my data table. I didn't create new columns for me. I can now save this as a new script, like really cool model, Box-Cox, and it's saved there. So when I replicate this, I don't have to go back through that whole process. It just becomes a neat way to transform that data without having to physically go in and transform your data. But there's instances where you do this and your data is just really messy and very far from normal, and you can't get there. And so we're going to go to that place in just a moment.